A very good morning to all of you. Okay, today we are going to learn the divergence theorem, or called as Gauss theorems. Okay, in the previous lectures, we have seen that to find the Flux integral. Okay, the Flux integral here, or the surface integral of vector form over a sphere. You have to divide the surface S to S1, which is upper hemisphere, and S2, the lower hemisphere. Okay, and to find the Flux integral on the cube, you have the 6 surface, then you have to do it 6 times. However, if the G be a solid with a closed surface, okay, for example, your sphere is a closed surface, or the cube is a closed surface oriented outward, and if let's say the F given by Mi plus Nj plus Pk, where the M and P have continuous first partial derivative on some open set containing G, okay, then the Flux integral by using the Gauss or divergence theorem, instead of you evaluate your Flux integral for sphere, where you need to do it 2 times, for cube you have to do it 6 times. Then if your surface is actually closed, then it forms a solid G, and then you can find the triple integral of divergence of F dv, across the solid G, where the divergence of F is actually del dot F. Del is a differential operator. If the F is 3D, 3D, then the del is a del xi plus del yj plus del zk, dot with the vector F. Okay, remember that the dot product, the result is a scalar function. Means you component I, you multiply with I, j with j, k with k, and note that I dot I is 1, j dot j is 1, k dot k is 1. That's why your del dot F, you get del m del x plus del n del y plus del p del z. So mean instead of you evaluate your Flux integral for sphere 2 times, cube 6 times, you just need to evaluate the triple integral of del dot F. Mean first of all you find the divergence of F first, later on become a problem of triple integral. For example 1, let S be the surface of the sphere x squared plus y squared plus z squared equal to a squared oriented outward. To use a Gauss theorem, make sure you have the surface is closed and oriented outward. So given the fxyz equal to zk, evaluate the Flux integral using Gauss theorem. If not use Gauss theorem, then you have to divide the surface S as upper hemisphere and lower hemisphere. Then you have to do it 2 times. Since sphere here is closed surface and it is oriented outward, then we can apply the Gauss theorem. So this is a sphere with radius a unit. To use Gauss theorem, instead of evaluate the Flux integral, evaluate the triple integral of divergence of F. So which is del dot F. So del is del xi plus del yj plus del zk, dot with your vector F. Your vector F in this case only consists of component k with the coefficient is z. Hence, we only del z we have 1. So this is triple integral of 1 dv across the solid G, which is a sphere, which represent the volume of the solid G. In this case, this is the volume of a sphere with radius a unit. That's why using geometric form, volume of a sphere with radius a unit, which is 4 pi a cubed over 3. No need to use your triple integral. Directly use a formula of volume of a sphere with radius a unit, which is 4 pi a cubed over 3. So you can notice that which is faster than if we evaluate the Flux integral on surface S1 is the upper hemisphere, S2 which is the lower hemisphere. Okay, second example, let S be the surface of the cube bounded by the planes x equal to 0, x equal to 1, y equal to 0, y equal to 1, z equal to 0, and z equal to 1, oriented outward. If not use Gauss theorem, you have to evaluate 6 times of your Flux integral on surface x0, x1, y0, y1, z0, z1, and add up this 6 result of your Flux integral. Since this surface is closed and oriented outward, we can use the Gauss theorem to find the flux of the vector field fxyz equal to 2xi plus 3yz plus z squared k across the surface S. Okay, so this is a surface of the cube where x bounded from 0 to 1, y bounded from surface k0 to 1, z bounded by the surface z equal to 0 and z equal to 1 is closed, closed and oriented outward, mean the flux flowing out. Then we can use the Gauss theorems or divergence theorem. So Gauss theorems means that the surface, the Flux integral f dot n ds across the surface S will be equal to triple integral divergence of f, which is del dot f dv, over solid G. So del is actually del del xi plus del del yj plus del del zk dot with your vector f given is 2xi plus 3yj plus z squared k. So evaluate the dot product first, which give you a scalar value. So which is del del x 2x plus del del y your 3y. Use different color. Del del y 3y, and then del del z del del z squared. So del del x 2x you have 2, del del y 3y you got 3, del del z squared you got 2z. So become 5 plus 2z, triple integral of 5 plus 2z dv, over the solid G. Solid G here is a unit cube. X bounded from x equal to 0, which is the this is a zy plane until x equal to 1. Bounded by the plane y equal to 0, which is the zx plane until y equal to 1. Bounded from x equal to 0, z equal to 0, which is xy plane until the top surface, which is z equal to 1. Hence, we use a Cartesian coordinate to evaluate this triple integral. dv, we use dz dy dx, where the z from 0 to 1, y from 0 to 1, z from 0 to 1. So first of all, integrate respect to z first. We have 5z plus z squared. Substitute limit of z from 0 to 1. So you have 5, we plug in 1 into z. When plug in 0 is 0. That's why you have total is 6 dy. Integrate 6 dy 0 to 1. Lastly, integrate to respect to x from 0 to 1. Integrate 6 dy, you have 6y. And then limit of y from 0 to 1 will get 6. Integrate 6 dx from 0 to 1. Lastly, you get the answer is 6. The third example, let S be the surface of the solid G enclosed by the circular cylinder x squared plus y squared equal to 9 and the plane z equal to 0 and z equal to 2, oriented outward. Use Gauss theorem to find the flux of the vector field fxyz equal to x cubed I plus y cubed j plus z squared k. The cylinder is bounded from z equal to 0 and z equal to 2. Hence, it is closed and the flux is oriented outward. Then we can use the Gauss theorems. Gauss theorem. F dot n divergence of f dv. So del dot f, this is del del xi plus del del yj plus del del zk dot with the vector f, which is x cubed I plus y cubed j plus z squared k. And then you del del x cubed, you have 3x squared, and then del del y cubed, you got 3y squared. And lastly, you del del z, z squared, we get 2z. And then we notice that this solid is actually cylinder. Solid is actually the cylinder, where the projection is the projection is actually a circle with radius 3 unit, because you have a cylinder. Okay, you have the cylinder, x squared plus y squared equal to 9, where the r is actually equal to 3. Hence, to solve that dv, we'll use a cylindrical coordinate, where cylindrical coordinate maintain the dz, and the dA become r dr d theta. Limit of z, because the cylinder is bounded from z0, z0 to z equal to 2. So limit of z will be from 0 to 2. So limit of z 0 to 2. Okay, dr, because this is cylinder, x squared plus y squared equal to 9. Hence, you have the projection of a circle with radius 3 unit. That's why your r is actually 0 to 3. R is 0 to 3. And then you rotate the r actually full cycle. So theta is from 0 until theta equal to 2 pi. Okay, so z 0 to 2, r 0 to 3, theta 0 to 2 pi, and then x squared plus y squared will be r squared. Then you factor out 3, and then x squared plus y squared, which is r squared. So plus 2z r dr d theta. So totally you have 3r cubed. 3r cubed integrate respect to z. So you got 3r cubed multiply z, 2z r dz. You will get z r squared. Integrate respect to z. So you have got z squared r, not integrate respect to r. Plug in the limit into z, because we integrate respect to z just now. So you got 3 times 2, 6r cubed. Plug in into z, so 4r. When you plug in 0, everything gets 0. And then secondly, integrate respect to r. So here you have 6r power 4. 6r power 4 divided by 4. So it becomes 3r power 4 divided by 2. Integrate 4r respect to r. I got 4r squared divided by 2. So become 2r squared. Plug in limit of r from 0 to 3. Here we get this is 3. You plug in r is 3. So we got 3 power 4, 81. So 81 times 3, 243 over 2. Plug in r is 3. So 3 squared 9, 9 times 2, 18. Plug in 0. Everything you get 0. And then lastly, this is constant where we get. Then lastly, integrate respect to theta. We got this answer multiplied by 2 pi, which is 279 pi. The fourth example. Let S be the surface of the solid G enclosed by the hemisphere Z equal to Z x a squared minus x squared minus y squared, and the plane Z equal to 0. Hemisphere. First example, you have a sphere. Now the fourth example is hemisphere. To make it close, this hemisphere bounded by the plane Z equal to 0 and oriented outwards. If you not use Gauss theorem, then you have to do your plug integral 2 times. One time is for the upper hemisphere surface, and another one is the surface Z equal to 0. So since these two surfaces are closed and oriented outward, we can use Gauss theorem to find the flux of the vector field given by x cubed I plus y cubed j plus z cubed k. So this is a hemisphere. This one is a hemisphere. So, the z equal sed a squared minus x squared minus y squared. Okay, because we plot it using mapper, we cannot put a, I put it as a 1. And the projections of the hemisphere is actually, you have, so this is a, because we plot using the mapper, negative a. This is positive a. Okay, this is negative a. Okay. When you square it, is actually you get a circle, sphere. When you square the hemisphere equation, you have x squared plus y squared plus z squared equal to a squared. Okay, for the projections R, which is on xy plane, z equal to 0. That's why you have the circle x squared plus y squared equal to a squared. So to solve the Flux integral here, so the Flux integral is using Gauss theorem or divergence theorem, will be triple integral divergence of f dv across solid G. Okay, and divergence of f is del dot f, where the del is del del xi plus del del yj plus del del zk dot with the vector f given, which is x cubed I plus y cubed j plus z cubed k. So, doing the dot product, you have the del del x, x cubed plus del del y, y cubed plus del del z, z cubed. So, you have 3x squared plus 3y squared plus 3z squared. Okay, factor out 3. So, you got actually 3 times of x squared plus y squared plus z squared, which is equal to radius of a sphere, which is rho squared. Okay, since the solid G is upper hemisphere, this type of a sphere, then we solve the triple integral using spherical coordinate. So for spherical coordinate, dv is rho squared sin phi d rho d phi d theta. Okay, where the rho is actually from the hemisphere equation that you square it, you get x squared plus y squared plus z squared is actually the rho squared equal to a squared. That's why rho is equal to a. Okay, rho is actually from origin until surface of your a. So rho is from 0 until rho equal to a. Okay, phi is actually measured. Okay, you measured the phi from z positive until your rho. So because rho, up to here. That's why phi for hemisphere, upper hemisphere will be 0 up to pi over 2. If for sphere, because you got the bottom, lower hemisphere, so phi will be 0 up to pi. Phi minimum 0, maximum is pi. For upper hemisphere, phi is 0 to pi over 2. Theta, because the projection is a full circle, which is x squared plus y squared equal to a squared. Okay, theta, you rotate one cycle, full cycle, which is 0 to 2 pi. So that's why you have here 3 times of x squared plus y squared plus z squared is rho squared. dv is rho squared sin phi d rho d phi d theta. Okay, rho from the center of the origin of the sphere until the surface of the sphere, which is 0 to a. Phi rotate from positive z axis until the bottom surface of z equal to 0, which is z 0 to pi over 2. Theta rotates your hemisphere horizontally, so you got 0 to 2 pi. Now integrate 3 rho power 4 respect to rho, where the phi is constant. So you got 3 3 rho power 5 divided by 5. So we factor out 3 over 5. Okay, plug in limit of rho from 0 to a. So you got a power 5. So 3a power 5 over 5. Okay, then now integrate sin phi d phi from 0 to pi over 2. You get negative cos phi from 0 to pi over 2. Okay, and you plug in phi is pi over 2. Cos pi over 2 gives 0. So minus, plug in 0 to cos phi. Cos 0 is 1. Hence, okay, negative here, you got positive 3a power 5 over 5. Integrate 1 d theta from 0 to 2 pi. You get answer is 2 pi. So total you have 6. Okay, a power 5 pi over 5. Cause here 3 times here 6. A power 5 pi over 5. Okay. So we have gone through 4 examples to illustrate the Flux integral using divergence theorems. To use divergence theorem, make sure the surface S is closed so that it forms a solid G, and the surface S must be oriented outward. Then the Flux integral, Flux integral f dot n ds is actually Flux integral of vector field. Since the surface S is closed, it forms a solid G. Then instead of evaluate your Flux integral, for example, let's say sphere, you have to divide your surface into upper hemisphere and lower hemisphere. Cube, you have to divide into 6 cube. If upper hemisphere, also you have to divide it into the curved upper hemisphere and the bottom surface, which bound your upper hemisphere there 2 times. So since the surface is closed, it forms a solid G. Then you can use the Gauss theorem or divergence theorem. Instead of evaluate your surface integral several times, you just need to evaluate 1 time of triple integral of divergence of f, which is del dot f dv across the solid G. But provided the surface S is closed and oriented outward. Where the del dot f is actually del dot xi plus del dot yj plus del dot zk dot with your component of your vector f. And we illustrate using 3 examples. First one is a sphere. If you're using normal Flux integral for sphere, you have to do it 2 times. And the second one is a cube. If without using Gauss theorem, you have to do your Flux integral 6 times. And then for the third one is a cylinder. Cylinder, you have the curved surface, which is cylinder, flat surface, which is z0 and z equal to 2. You have to do 3 times. And then the fourth example is a upper hemisphere bounded by the plane z equal to 0. Without using Gauss theorem, you have to do it. Surface 1 for upper hemisphere, surface 2 is the plane z equal to 0. So using Gauss theorem, instead of doing your Flux integral several times, because the surface S is closed and oriented outward, then you just evaluate triple integral del dot f dv. So dv here depend on your solid G. If like cube, then you use a Cartesian coordinate. If you got cylinder, then you use cylindrical coordinate. If you have sphere, upper hemisphere, or you have the cone, then you can use your spherical coordinate. Cone with combination of sphere, you use cylindrical coordinate. If only cone, bounded by the flat surface, you may use a cylindrical coordinate. With this, thank you for attention and watching this video.